Hello. Today we're going to be going over the fifth lesson, which is coding in FTC. So the four main aspects of coding within the first tech challenge is first mechanism programming, which controls all the robot's mechanisms. The second is movement, which enables movement through controllers and through autonomous trajectories. The third is through sensors, which makes use of sensors for enhanced accuracy and consistency. And lastly is for control, which is to add precision to all of the robot's processes. So the first section is mechanisms, where we have to add functionality to individual mechanisms on the robot. Most mechanisms are controlled by motors, which are either servo motors or DC motors. They're often programmed in conjunction with sensors, and mechanism programs involves adding functionality and accuracy to these motors that control them. Some enhancement to mechanism programming can include multi-threading and finite state machines as well. So the first step is how to code a motor, specifically a DC motor. So the code on the right, as you can see, has a function which says set mode, which is run DC motor dot run mode dot run using encoder. Um, this basically turns the parts of this program turn the motor on and off with different speeds. And a motor has the ability to be turned in both directions with variable speed inputs as well. So some functions that you will commonly use with when using a DC motor is run to a position, which is where the motor attempts to rotate to whatever direction and position is necessary to go to the position that is specified. This is using the inbuilt encoder within the motor. The second function is run using encoder, which again is the motor's where the motor does its best to run at a targeted velocity. Um, Run without encoder runs the motor at whatever velocity and by just applying some amount of power to that motor. The stop and rest encoder is where the power in the motor is set to 0, and the encoder position is also reset. The next is how to program servos. In the right side, you can see code that also programs a servo, specifically here where it says servo.setPosition and in parentheses position. The servo.setPosition function can help program the servo to move to a specific point within its given range of motion. Um, It is important to note that servos can be both continuous and non-continuous. A continuous servo can go to a specific position as mentioned with the set position function. A continuous servo, on the other hand, can only be turned on and off and just spins in either the positive or negative directions. The next part is movement, which is where we try to create precise and sometimes even complex trajectory sequences for the robot to follow autonomously. The purpose of the pre-programmed movements is mainly for the 30-second autonomous period, where the robot can only move through pre-programmed instructions. Um, Pre-programmed movements allow the robot to perform more complex movements like splines, linear heading changes, and accurate strafing, which are difficult for drivers to recreate. This is why it helps drivers during the teleop period as well, where it allows efficiency and also reduces driver error if used correctly. So the implementation of using this motion software requires a robot to be tuned, specifically the drive constants that are part of it. Um, Drive constants are specific to each robot and are very dependent on the position of the different odometry pods, the final weight and size of the robot, and often they can take a lot of time to gain consistency with. So there's a lot of processes and tests that are listed on the Roadrunner Quick Start, which help you tune all of these different constants. The entire tuning process is listed and explained on learnroadrunner.com, which also teaches you how to download and get started with the Quick Start. So what is PID? So PID stands for a proportional integral derivative. Um, what that basically means in simple layman terms is whenever the robot is trying to follow a specific path and encounters any error from that path, it is processed using a KP or a constant P, a constant I, and a constant D. And using these three constants, it uses some pretty basic calculus to then create an output power that is provided to the robot and the four motors. This is largely based on encoder positions, which it derives through its odometry. PID controllers has three parts which must be tuned. So let's look at some PID applications. Um, One application of PID that is used quite popularly is for linear slides, where linear slides need to reach a specific position, which oftentimes encoders cannot do so well by themselves. And that is why by using PID, error can be corrected for using the encoder values to reach the correct destination. Similarly, it can be used for just running motors themselves, potentially for arms and other components, and also for the drivetrain, which is also composed of four DC motors. Trajectory sequences are ways that the robot basically plans out a path for its entire motion profiling algorithm. So so motion profiling basically allows velocity control and also allows you to maintain or rather apply a maximum constraint on acceleration and angular acceleration. So using trajectory sequences does require tuning to be completed, which means the robot has an accurate connection between itself and its position on the field. All trajectories and their purposes are also listed on the learnroadrunner.com website, which you can obviously reference from that link. The third part is sensors. Making use of a variety of sensors for consistency and accuracy is really beneficial in a precise challenge like the first leg challenge. So the first sensor that I have also mentioned previously is an odometer. And what an odometer actually means is it's a way of measuring the distance a vehicle has traveled. So in the context of FTC, teams typically use 2 to 3 odometers, and they are used to measure the X and Y coordinates of the robot. Um, so odometers can either have mechanical or computerized components. So some examples of an odometer is obviously like cars that we drive around every day have odometers in them, and that helps keep track of total distance of every drive that the car goes through. And as you can see, at the bottom of the speedometer dial is the odometer as well, which counts the total miles that the car has in its lifetime. So the main purpose of odometers, again, for this challenge is to determine the position of the robot based on the distances that it has already traveled. It's very useful and fairly it's pretty irreplaceable when it comes to autonomous path following and the entire autonomous period. Um, So what odometry basically lets the programmer do is turn the entire field into a coordinate plane. Wherever the robot starts is the origin, and the target location can simply be specified in X and Y values of inches. So some parts of an odometer are the encoder, which is obviously the main component that tracks the position itself using ticks. Next is the casing, which holds the omni-wheel, the encoder, and everything together and mounts it onto the robot. And lastly is the omnidirectional wheel itself. The omnidirectional wheel is special because when moving in a forward direction, it rotates, but when moving sideways, it's able to move on the little rollers that you can see on them without actually causing any friction to the robot itself. So in this image, you can see there are odometers between the two purple wheels on this robot. And typically a robot will have two odometers, as you can see in the image. So, positions of an odometer on a robot. Odometers 1 and 2 can be used for changes in the forward direction of the robot, and odometer 3 can be used for measuring changes in the horizontal direction of the robot. Um, Using two odometers for the forward direction is helpful because it also allows us to implement another function of calculating our heading. But I'll go more over heading calculations later. So how an odometer works is the encoders that you can see in the odometer casing itself. They record the movement and the turns of the dead wheel inside the odometer. Um, that information is sent to the control hubs where these odometers are actually directly wired to the control hub. And using these inputs, the control hub calculates the actual location of your robot on the field. So odometers do need to be trained before they can be not tu trained. They need to be tuned before they can be used. A very popular sensor that is also used in the FTC challenge is a camera. Camera can be used for both April tags, barcodes, and also for identifying unique elements that are on the field. It can be used for specific parts of the challenge, like autonomous randomizations, or even used for identifying specific parts of the field to localize the robot again. Cameras can be used to measure color, distance, and even ratios of both when being used on a robot. So some other sensors that are used. Um, Another popular sensor that can be used is an ultrasonic sensor, where the sensor emits sound waves and calculates how long it takes before that sound wave reaches the sensor again, effectively allowing it to identify the distance of an object in front of it. A touch sensor can be used to identify if there's contact between two surfaces, as it's effectively functions as a button. The IMU, or internal measurement unit, is a sensor that is a combination of a gyroscope and accelerometer that allows the robot to calculate its heading. So if a robot does not use a three-wheel odometry setup, it can instead use an IMU for calculating the actual heading. Next up is the potentiometer. A potentiometer is a device that measures the output voltage um of any part of the robot. It can be used to measure voltage of a battery or also the current draw of a motor. And it's helpful to identify if any parts of the robot are drawing additional current than they should be. Lastly is a magnetic touch sensor, or a magnetic limit switch, and it is used to detect the proximity of a magnet near the sensor. Last but not the least is enhancing the control when programming in FTC. This can be both for the mechanism and for the robot movement itself. So the first thing that we have already discussed is encoder counts. So every motor has an encoder that can be used to identify how much the motor has moved in what direction. An encoder basically converts motion into a digital output that can then be processed by a control hub to identify how much the motor has actually moved. And it is essential in controlling motor movements through the program itself. Next is PID. Um, I had touched up briefly on what PID does before as well, but PID is a very beneficial in terms of precise mechanism and robot control. It is a way for the robot to make corrections solely based on error of encoder count reading, based on where it should be and where it actually is. The three terms in this are the KP, and the KP effectively multiplies the amount of error that we have with a constant itself to identify how much power needs to be applied to overcome that error. The integral term is a way of measuring error that is accumulated over time. Even if the error is small in magnitude, if it is a sustained error over longer periods of time, the integral term continues to increase and thereby is able to add corrective power into the mechanism. The derivative term calculates the rate of change of error. So in a case where the robot is either accumulating or correcting for error, the derivative term helps smoothen out that slope to make sure that the robot does not overcorrect or go into loops of oscillation by having too high a rate of change. A lot more detail can be learned about the entire tuning method through the Control Alt FTC website, where they talk about the entire creation of a PID algorithm from scratch. Next up is multi-threading. And multi-threading is a technique used through code in which we basically allow two parts of a program to run in a non-linear fashion. This allows multiple simultaneous code processes to run together at different stages of themselves. So it is quite useful in programming multiple mechanisms synchronously together, and it helps increase the efficiency and speed of the robot. A tutorial that explains multi-threading better can be found at stemrobotics.cs. Next up is finite state machines. Finite state machines are basically a way of maintaining a number of states that the robot is within and help the robot transition between these different states based on certain commands or conditions. It allows multiple complex actions to take place in a non-linear fashion by switching states. Individual actions within the state machine depend on the completion of other actions to execute, and a more detailed explanation of this can be found at the gm0.org website. Thank you so much for watching.